Hi, we're Project Group 14, and we semantically segmented 3D Gaussian splats using transformers for our project. This issue can be addressed in two ways. One way, you treat it like a classification problem and give the model semantic categories beforehand. In the other way, the model just responds to a free text prompt. The significance of this issue is that it can be used to enhance driver and pedestrian safety on the road with autonomous vehicles by detecting pedestrians, or potentially help in assisting with detecting brain tumors in the doctor's office. The novelty of our approach was that we deviated from a convolutional neural network, which a paper that we looked at already used, and swapped to a transformer-based architecture because we believed it would lose less information.
Coming to methodology, our work is mainly the re-implementation of semantic Gaussians. As you can see on the left side of the image, which shows the existing approach, it involves a voxelization step that converts 3D Gaussians into a discrete grid before it passed to the Minkowski-net architecture. And this loses a lot of information, especially the geometric features, and this affects the semantic accuracy. Our approach is mainly replacing the Minkowski-net architecture with a point transformer so that we can directly use 3D Gaussians by preserving these geometric features and avoiding the step of voxelization. And this improves the semantic accuracy. We are using ScanNet 20 dataset. It has around 1,500 scans of indoor environment and has 20 classes. For this project, we are using only 20 classes because these files are huge in size and it requires a lot of training. It requires pre-processing as well because these files are compressed .sense files and needs to be converted into ScanNet format. After we process, we get the following files, which are like RGB images, depth images, 4x4 camera to world pose matrices, which is used for training the geometry, intrinsic matrices for projecting 3D Gaussians onto the 2D image plane. We also require ground truth semantic labels, which are used for creating the S2D semantic embeddings, which will show in the further slides. And we get initial sparse point cloud, which will be used for initializing the mean of each 3D Gaussian.
In this section, I'll be talking about how the 2D and the 3D embeddings were generated for the semantic Gaussian paper and how we drew inspiration from that for our project. The 2D embeddings in the paper were generated using various pre-trained semantically labeling models, such as CLIP, but those models are just for 2D images. These 2D pre-trained models were coupled with segmentation models, for example, SAM, to generate the ground truth. There are several other combinations of semantically labeling 2D models, such as LSEG and OpenSEG, were also used, but we found that the CLIP and SAM combo was the best. For the 3D embeddings, sparse 3D convolutional neural network was used, particularly Minkowski-net, which were treated as the labels and trained over the training period to generate 3D embeddings for a 3D space. This is how the training pipeline looks like after developing the 2D embeddings. The cosine similarity is tried to maximize, which results in minimizing this particular loss. After achieving particular sufficient threshold for errors, the 3D embeddings are used to render a 3D space.
Here are some results. We trained both models on 20 scenes for 200 epochs, and you evaluated them on 5 scenes. And you can see that point transformer was much better with a 63.4% improvement on the mean IOU and a 42.5% improvement in the mean accuracy. And for each class, these numbers are the IOU. The point transformer was better on almost all of them, and the ones it wasn't better on, it was only worse by a small amount. These are two images that we segmented with both models. And you can see that the point transformers segmentation is much closer to the ground truth, especially in this segment. The second image is able to segment out the pink table and yellow chair quite well. So it was much better. So yeah, in conclusion, the point transformer outperformed Minkowski-net, and we think this is due to differences in the inductive bias in both models. Minkowski-net is just a CNN, while point transformer has attention, which allows it to capture a longer range uh, contextual dependencies within the 3D space, which allows it to segment it out better. And this points to transformers as a new paradigm in solving 3D open segmentation problems such as healthcare, robotics, etc. Thank you.